hurry and finish this. Hurry in a good way. And starting Monday, I'll do a review. If I don't have time to finish Monday, I'll do a little bit more on Wednesday before I start new material. Does that make sense? Okay. So you also should have noticed you have assigned another homework assignment. Okay, it's relatively short. It's problems like we're going to do today. I want paper copy, and I gave you until Wednesday to turn it in. So in addition to this, I'll also post an example, a solved example as well online to give you a little bit more practice for the exam. And one thing though, because the exam is coming, I will kind of require you to submit your paper on Wednesday, meaning I will accept it late, but not after 4 p.m. on that day, because I want to post out the solution for you guys to take a look at it before the exam. So the other thing, I'm not going to be able to grade it, so if you want to look at what you've done compared to the solution, you can just snap a few pictures of what the work you've done, okay, keep it so you can compare. Does that make sense? Okay. So last time we talked a little bit more about forced vibration. We established a few rules and introduced a few new concepts. Okay. What we did establish is when a forcing motion is causing the product motion, we had 3 rules. Okay. The first one was that everybody will vibrate at the force frequency. That is so important. When you shake something, it will vibrate at that forcing frequency. That's the first rule. The second one and the third are very synonymous, very close to each other. They're not synonymous, I should not say that. They're very close. One is for amplitude. It just says that the output amplitude was proportional to the input amplitude. And the relation between the two was the magnification factor, which is plotted here. Lastly, we add that the ratio or the output acceleration was also proportional to the input acceleration with the same factor, which is the magnification factor. So we looked at this equation, we draw it, okay, take a look at it, and this is important here. Remember that this is the absolute value, because when that ratio, which we use on the x-axis here, pass the value of 1, this is 1 here, so it becomes negative, okay? So you have something that will go like this typically. It's nicer to represent it as an absolute value in this way. So what we mentioned is that what we notice here is that when the ratio of the force to natural frequency gets close to 1, you end up with a large magnification factor. That means an input gets amplified quite a lot. And that region here, close to 1, is what we call resonance. To illustrate that, we watched a little video where we had a series of weights, okay, with basically metal bars that basically behave the same way as spring and mass, okay, but entered resonance at different frequency as the force frequency got closer to their own natural frequency, which is a characteristic of their system. All natural frequency for a spring and mass system, which we're going to use, is 1 over square root of k over m. Okay? So we looked at this and also look at here when we have a very low frequency, basically everything follows together. Okay? You don't have any absorption of the vibration by the shock. So any input is equal to any output is equal to the input. And as you progress, things change. And at some point, okay, which is here, okay, depending on the system and the characteristic, most of the vibration get actually absorbed by the cushioning material. Okay, that's what we've seen. So let's say you have a mass and you have the force vibration applies here, and you have a cushion or a spring here between the two. This will vibrate, but everything is going to be absorbed by the spring. Okay. So, not everything, but you may have a small movement when you have a large movement here. as this point is where the magnification factor becomes less than 1. So for any input, the output, okay, is lower, okay, which is perfect, okay. Obviously, we don't pick a cushion to protect against vibration, remember that, okay, but if your cushion does get in the zone where it protects against vibration in addition to shocks, that's a plus. So that's what we talked about quite a lot last time, and then we started to work on some problems that I passed around the other day. So for the first problem, which is example 2 here, we had a mass on a cushion system with a spring constant, and what we did just before we left is we calculated the magnification factor for the spring and mass cushion. We had a value for the magnification factor of minus 3.89. So that means that this system is out of phase, okay? So you're on that side of the magnification factor. So when the movement is going up, the product is going down. So you have something like this. So what is asked in that question, okay, is to find the maximum amplitude and acceleration experienced by the product. So let's see. We had the force frequency was given to be 2.5 hertz. And we had a maximum acceleration, okay, which was from the input, and that was 0.1 g or 0.981 meter per second squared. So what we have to do now for the product, okay, we're looking for the output now, okay? So this is actually pretty straightforward. So the acceleration of the product, which is the output acceleration, is going to be equal to magnification factor times the input. So if we were to multiply these together, you'll find a maximum acceleration here of minus 3.81 meter per second squared. Bless you. So again, the magnification factor is what allows us to go from input to output. The last part, okay, is ask you to find the maximum amplitude, okay? So how would you calculate this? We don't have much information. So do we have a relationship or an equation that links acceleration and amplitude?
The ratio.
Okay. So if you remember, we had that acceleration. Maximum acceleration was a p squared. Okay. So that's what allows you to link both of these. Okay. So that amplitude here, okay, if you're talking about the output, is going to be equal to the output acceleration over p squared. Okay. So a 0 over 2 pi a frequency squared. So what frequency are we using here? Do we have to use the force frequency or the natural frequency?
Natural.
Who votes for natural? 1, 2, 3. No. So remember, here the product, is it vibrating at its natural frequency? It's not, okay? It's vibrating at the force frequency. The natural frequency is a characteristic of the system that will tell us for any force frequency what kind of magnification I'm going to get between an input and an output. But everything vibrates at the force frequency. The only time that it's going to vibrate at the natural frequency is when you have a 3D vibrating system, okay? If you have that spring and mass and I compress it and I let it 3D vibrate, okay, that's going to be the case. But if I'm forcing the motion, okay, it's always going to vibrate at the force frequency. And that's very important not to forget this, okay? That's a classic mistake. So if you plug in all the numbers in here, you'll find that you'll have a maximum amplitude here of minus 0.0154 meters. And again, here, you can carry the negative sign if you want, but you don't have to. I don't mind this. The negative is there not just to illustrate the link between the forcing motion and the output or response. So if there's a difference in sign between the two, that means they are going in opposite direction. They are out of phase. And if the same sign, that means they are in phase. So hopefully this is pretty straightforward. So let's do the next exercise. Let's bring it up to the next level. Actually, it's definitely the figuratively and actually really the next level. So what you have in this case, okay, you have a large light bulb, okay, it can be for a big outside flood lamp or something like this. It's transported by truck over a long distance, and you have a major vibration associated with the truck at a frequency of 4 hertz, okay? So, and a maximum acceleration of 5g. So, truck, okay, as a frequency, and that's going to be the forcing frequency of 4 hertz, okay? And as a acceleration, this is going to be the input of 0.5 g. So a lot of packaging application, okay, they will use g's for acceleration. You can keep it in g's, but I personally like to use meter per second squared. Good. The static deflection of the light bulb on the cushioning material is 1 centimeter. Okay, so this guy here is what we're going to call the product. Okay, so we are given a static deflection 1 centimeter, 0.01 meter. Make sure you convert centimeters to meter right. It's pretty straightforward, but it's a classic mistake. Also, the light bulb filament, which is a critical component, has a natural frequency of 3 hertz. Okay. In addition to that, we have the filament. Okay. And this is what we call the critical component. Okay. This guy has a natural frequency of 3 hertz. So let me just I'm going to put a C here for identification, that is the component. So find the frequency, maximum amplitude, and maximum acceleration of a forcing motion, the product, and also the critical component. So now we have a problem that is a little bit different, okay? So if I draw this very simplistically, okay, try to do a good light bulb on the side here. Okay. It's a super classical light bulb. Okay. Like this, and it sits on a cushion like that. Okay. Just imagine a big one. Very heavy glass. So what we have now is that on that bottom here, let's say you may have corrugated here, something like this in the box, and then the truck is vibrating, okay? So from this to the product, okay, you can represent this something like this. This would be the product. Now, the critical component is inside the product, okay? So it's a different level. So in this case, if you put yourself in the product, in the component's place, okay, what do you think is going to be the input for you? Is it going to be the movement of the truck, or is it going to be something else?
The movement of the truck.
I'm sorry?
The movement of the truck.
For the filament, let's say you just like you miniaturize yourself and you're going in there. I don't know why, but you're there. Okay. What you see moving, okay, is actually the light bulb. Okay. Does it make sense? So your movement, okay, depends on the movement of the product. So if you have something like this, it's a two-step problem. Okay. You have first a relation, okay, between the forcing motion, so this will be the truck, and here we have a certain magnification factor that will allow you to go from that input to that output. But from here to here, okay, you're going to have a second magnification factor, okay, and you're going to have, for this guy, his input is going to be the product. Does it make sense?
Oh, so you're saying there's two things that can break, pretty much?
There's millions of things that can break, but in this case, the glass, it's not going to shatter, okay? But what is critical in this case, and that can vibrate and break, is the filament, okay? So just think about the gas chromatograph, okay? That thing can vibrate, okay, as a whole. But there's a bunch of components in there. Piping, okay? You may have printed board and all of these things, okay? They're going to vibrate. Each of them are critical, are components, okay? They're all going to have their natural frequencies, okay? They may all subjected to damage depending on what's happening, okay? So, but if they are inside the product, for them, their input, what drives their motion is the movement of the product. It's not the movement of the truck bed. Does it make sense? So, it's the same thing as this. It's just one more step, okay? So, if we go and start figuring out things, okay? For the product, we only know the static deflection here. But obviously, to go from here to here to here, okay, we'll need magnification factor. So on this guy here, I know the frequency and I know the acceleration. So I can calculate the amplitude relatively easily because we have done that right there. So once I know all of this, okay, then I can use a magnification factor to go from the truck to the light bulb, and then a second magnification factor to go from the light bulb to the filament. What I need, though, to go from here to here is a natural frequency. So the natural frequency for the product, okay, P is for product, and C is for the component. You can name that 1 and 2, A and B, whatever you want. I don't mind. So 1 over 2 pi. Typically is K over M, but we're given the static deflection. So this is the gravitational acceleration over the static deflection. It's one of the equations we worked on before. So if you calculate this, you can find a natural frequency of 5 hertz, okay? And here G, in case you don't remember, okay, 9.81 meter second squared. So, if we start from the beginning, okay, and we have the truck, I don't know, if you have space on your sheet, you can write, keep that there. You don't have to rewrite all of this, okay. With the force frequency of 4 hertz, we have the acceleration of 4.905 meters second square, and our amplitude is going to be given by that acceleration over 2 pi force frequency squared. If you calculate this, let's see what I get here. We have a value of 0.0078 meters. So that is describing the entire truck movement. The next step now is to go from the truck to the light bulb, okay? So let's find the magnification factor between the product and the truck. So we're going to call that M1, and in this case it's going to be 1 over 1 minus, now it's our equation, the force frequency in this case is established as 4 hertz. It's going to be divided by the natural frequency of our product, okay, which is 5 hertz. And again, I said the product, but it's the natural frequency of the cushion and product itself here, okay? Square. If you calculate this, you find a magnification factor of 2.78. Again, in your exam and homework, don't carry like 10 significant figures. It's not a big deal, okay? 3 significant figures is usually plenty of accuracy for what we're trying to do, okay? So knowing this, we can fully establish the movement of the product, okay? So first thing, the frequency at which it's going to be moving is still going to be equal to the force frequency. It's going to be 4 hertz. It's all vibrating at this. Now, in this case is output acceleration, okay? Here is going to be equal to m1 times the input that we established before. And that means here, if you replace these values, you'll find for 2.78 times 4.905, and that is going to be equal to 13.6 meters second square. M, sorry, if it looks like this.
For the F, is that 4 or 41?
What? Sorry?
For the F, like F of F?
F of F?
Yeah.
Yes, it's 4.
What are the units?
Hertz. Hz.
Oh, okay. Okay.
Yeah.
That's it.
Sorry. So, to replace all these numbers, I don't have to plug it up. Actually, you get the 0.0217 meters. So that defines all the movement of the product. That's what I was asking you to do. That's it. Now, for the critical component, the input is the movement of the product. So that means, for this case, you need to understand that what was the output now, okay, becomes the input, okay? So we can find a different magnification factor here for this guy. So it's going to be 1 minus. So what would be the frequency we're going to use here? What would be that ratio? What is it? 4 over 3. You guys agree that it's still going to be 4 here, or we're going to use 5?
4.
4. Very good, okay? Everything will vibrate at this, okay? Frequency is a force frequency. So we'll do this. I'm trying to enforce that because that's an easy mistake to make. It's so easy. Just everything is forced is at the same frequency than the driving motion. So when you do that, you'll find a value of minus 1.3. Means it's out of phase, okay? So then for this guy here, for the critical component, frequency is going to be the force frequency for hertz. Its acceleration is going to be m2 times the acceleration of the product. So that will be 13.6, okay? So I didn't put AI here just to make sure it's not confusing in any way. So you'll find here a value of minus 17.7 meter second square, and you're going to find a 0 and 2 times 0.0217. Sorry, can you guys read at the back, or is it too low? Good. 0.0217. So that gives us 0 minus 0.0. I'm sure now you cannot read because I'm in front of it, but I'm going to move away. 202 meters. That's movement of the critical component. You guys have any question on these? I'll let you have time to finish.
On the previous problem,
Yes.
to get the amplitude out, we use the A out over P squared.
Yeah.
Is that equivalent to?
Yeah. It should all work together. But the thing is, once you have, if you start with that relationship, initially we used it to find a relationship between the amplitude and the acceleration. Once you have a set of both that we added for the truck, it's a lot quicker to use the magnification factor because it's just multiplied by a constant instead of doing the. It's not a lot of work, but yeah, I feel it's easier that way. But yeah, one way or the other, it's gonna work. So this is kind of the simplest step I can take to go from including a critical component, a problem like this. Now, the other thing you have to think about is there's no many equation here. So the only thing I can ask you is going to be very similar to this. So the equation you have to deal with, okay, is the magnification factor. Okay, so you have this guy. I forgot to post the equation sheet. I'll do it today. So you have this guy here. Okay, you have this guy here, square, and you have the natural frequency equation. So that's basically it, okay? So whatever I'm going to ask you to do, it may be a little bit different, but it's going to be to find one of these values somehow related, okay? One thing that is important as well is this. Okay, so the magnification factor again allows you to go from input to output, okay, between two different levels. And at one level, the relationship between acceleration and amplitude is given by this. So I can ask you sometimes to find an actual frequency or find something in there, but that's it. That's the essence of these problems. So should be relatively straightforward. So again, you have a practice with the homework. I also post another practice problem with a solution for you guys to do one more, but there's going to be something like this on the exam, okay? It's going to be like this. It's going to be very similar. You're going to have a product and a component that you will have to work on. Good. Any question on this? Okay. So the next step I wanted to do, okay, is I usually do it before, but I wanted to make sure I covered all the materials here before I go through this. Is I want to work out with you where this thing comes from, okay, and how we can get that from a force balance on our system, okay. So let me write this down. Undamped forced vibration. That's what we're working on. There's no dampening at this point. Okay. Yeah, look at magnification factor. as you know, you have a certain mass M, okay? And for force vibration, you have like a certain input here, okay? And we can write as AI sine of PF times C. And this guy here is the movement of our product. It's x of t that we're trying to describe. So very similarly to what we've done, for the free vibration, if we sum the forces on the x in the x direction, okay, here, that must be equal to the mass times the acceleration, okay. But we have as a force, we have only two things on our mass here, okay. We have the force of the spring, okay, minus the weight, okay, and that's going to be equal to the mass d squared x dt squared. So last time, the force of the spring, we wrote it as minus k, and it was x of t, or x, minus the static deflection. So that doesn't change. Now, the thing that's going to be coming next, okay, is to understand that in addition to this term, okay, now the bottom where the spring or cushion is sitting is going to be moving up and down. So that means that if actually it's moving in the up direction, okay, it's equivalent as if it were static and the x is going negatively, right? Okay? If it goes up, it tends to compress the spring. If it goes down, it tends to stretch it. So to include that into the force of the spring, because that force vibration is involved in the force of the spring here, okay, we have to subtract it
Can you say
here.
that? Can you say that one more time? I couldn't see.
What is it?
Can you say that one more time? I couldn't see because I was looking at your
You
back.
couldn't see?
I was looking at your back.
Okay. Oh, sorry. I'll just write this and I'll explain this. How's my back? So we have to correct for this input movement there, this way. So let me re-explain this. I'll have time to finish writing this. So in the free vibration, this was gone, okay? So you only have this because you were compressing it and releasing it. Now, as the bottom here is moving, okay, you can just for a moment picture that this is fixed, okay? So when this is going up, okay, it's equivalent that if it was steady and this was going down, right? For the spring itself, it doesn't care where's the compression coming from. So that means that if this is going up, that tends to add to the force of the spring in the compression, okay? So it basically inverses. That's why we need a minus sign here as well, okay? And just think about it, it's going to make sense, okay? So that's where we include that forcing motion is in the force of the spring, okay? If it's going down, that's tend to decrease the spring, okay? If we're working compression, so it's going to be negative, is going to tend to go in the effect of being an x going in the positive direction. So that's what happens in here. So the static deflection, you should remember now that this is the weight over the spring constant. That's why it's always going to simplify with the weight here, okay? And we know that piece of F, okay, is just 2 pi times the force frequency. Yeah, 2 pi times the force frequency. And here, let me just make sure that you guys know this is forced frequency. Okay, so the next step, as you can imagine, partially from this, is to multiply the k through here. So I'm going to drop the t here because we understand that k that x is a function of time, and that'll be plus k. And here you're going to have w over k, like this. It's going to be plus a sub I k sine, actually I should write this k a sub I sine of p sub f times t. This minus w equals m d squared x dt squared. Let's see if I can use color. This doesn't look like a k, but it is a k. So those two k's will simplify like this. And the plus w with the minus w cancel out. Okay? Once we reorganize this a little bit better, okay, we can write, let's do that in one shot. We can write d squared x dt squared, we divide by the mass, okay, that will be equal plus k over m times x, that will be equal k over m a sub I sine f. Okay, so this is similar than what we had when we were dealing in free vibration. I don't know if you guys remember, but what was the difference between this guy and when we're dealing with free vibration? There was only one difference. You guys remember? You blocked it out of your mind already.
One term.
So
The right side?
the right side, right. So what were you saying? It was homogeneous. Very good. Okay. In this case here, it's not homogeneous. Okay. Typically, on the right-hand side of these equations, that's what we call the source terms, right? This is when creating the motion. So it is a non-homogeneous linear second-order ordinary differential equation. Blah blah blah. Okay, that's probably what you heard. So it's important, though. Okay. So constant coefficient, second order, because the derivative, the highest order derivative is from the second order. Okay. Again, constant coefficient. And it's not homogeneous, okay, because it's there, and it's ordinary because it's a function of only one variable, as if x is a function of time only. It's not partial. So, if you x of of t, if you remember, in those cases, you can find the solution, the homogeneous solution, and a particular solution, and the sum of them is the general solution. So this would be what we call a particular solution, and this is the solution to the homogeneous problem that we already done. Homogeneous solution. So x of h was obtained in the case of a freely vibrating system. So what we had is the homogeneous solution was an amplitude for the homogeneous problem, sine b of the natural frequency in this case, t plus a certain phase angle like this. Okay? And p sub n was just 2 pi times the natural frequency, and that was equal to square root of k over m. All of this is we've done the other day when we studied the free vibration system, from which we obtained that equation for the natural frequency. This is where it comes from. Now, let's see. So that being done, okay, typically when we want to find a particular solution, we look at the non-homogeneity and we try to figure out a term that's going to be similar to this. Okay, if you have a polynomial, it's going to be a polynomial. Obviously, if you have a sine times a certain constant, it's going to be a sine or a cosine function, right? It has to be, okay, some sort of something of one type of these functions. So what we're going to do here, okay, let's assume a particular function, a particular solution of the form P equals AP, which is going to be a particular amplitude, okay, sine PFT. Again, we cannot go away from that frequency because whatever we have here, okay, if we derive it and add the constant to the same function, we cannot get a different frequency. It's going to have to be the same frequency. So if we start with this and we try and see what happens, if you derive this twice with respect to time, to replace in that equation here, so this will be minus AP times that forced angular frequency sine of PF times T. So that's kind of nice because obviously we're going to have a sine for x here. We're going to have a sine here because we derive twice, and we have a sine there. So it just, you should all cancel out nicely. So, sorry, this is xp. So if I call that 1, introducing xp and d square xp dt squared in equation 1, what we get, okay, is, so d square x dt squared is this, so minus ap pf squared sine pf times t, okay? Then that's going to be plus k over m, and that's going to be times this guy here, ap sine p sub f times t, and all of this will be equal to k over m, ai, sorry I'm running out of space here, sine p sub f times t. Mistake here. Let's see. Almost done, guys. So that is the nice thing here with our assumption that all those sine function vanish like this. And again, if you don't remember, this here is d squared x p over dt squared, and this guy here is just our function x of p, okay, that we're replacing our equation. So with this established, what's left is minus ap p sub f squared plus k over m ap equals k m times ai. So if we take that or group them together, what we're going to get is minus p sub f squared. Oh, let me just do this here. Just a quick reminder. Pn squared is actually equal to k over m. Okay. So that's from the 3D vibrating system. I don't know where, right here. So the natural frequency, okay, is a ratio of k over m. So if you have the square root of k over m. So if you have k over m, that's this guy squared, okay? So in here, we can replace this by that natural frequency angular expression, okay, on each of them. And it starts looking more and more like our equation we are after, the magnification factor. So AP here this, and we can obviously reorganize this as a sub I 1 minus PF over PN squared. So in here, what I did, I just divided numerator and denominator by Pn squared, and you end up with that expression. So that means that XP, okay, is going to be this guy here. We were able to find a particular solution to our system. Now, the real solution, I do have a few minutes. 2 minutes, we're good. X of t is H, the homogeneous solution plus the particular solution, okay? So, this is therefore n sine PNT, okay, plus what we just derived. Now the thing, what happened in this problem, we have an undamped system, okay? In real life applications, okay, this part gets damped out with time. So if you have dampening, which happens in any real system, that homogeneous part of the equation is going to disappear with time. Okay, you're going to have an exponential function that's going to decay with time. It's going to vanish. So for long exposure to that extensive exposure to a force frequency, you end up with only this. Okay, and that means I'm going to write this as the last thing here. The maximum value for the displacement is what's called our output. Okay, as we defined it before, A sub O. And that's going to be equal to A sub I 1 minus this guy here. So 2 pi force frequency, 2 pi natural frequency squared. And that's our final equation in a way. So we have from here that output over input is what we obtained, or what we used before for our analysis. Okay? This is the magnification factor. It's also equal to that ratio of acceleration. So obviously there's a few assumptions here, but that's where that thing comes from. Okay? I'm very surprised that no one actually asked me if you will have to do that on the exam.
Derivations?
Yeah?
Derivations?
Yeah? I'm just wondering because usually that's one of the first questions the student asks me. Is it going to be on the exam? That's, by the way, I don't know if you know this, but that's one of the most favorite questions for all professors to be asked. Is it going to be at the exam? You want to know the answer?
Yeah, it's not.
Let's reconvene on Monday. No, what is it?
I just assumed you did it on all your other ones.
Okay. What did I do on all the other ones?
There might be an answer.
Okay. So my goal with this, okay, is it's not, if I ask you a question on a derivation like this, okay, it's going to be a bonus question, okay? My goal, why I spend time in class to do this, okay, is to, as a student, like, I know you have to go, you can go, but as a student, I hate it when people just give me an equation and say you have to use it, okay, without explaining where it comes from, okay? So I try to show you the rationale behind these equations. And I think as engineers, it's important that you should always question these things because they rely on assumptions. And if you don't make the right assumption, you won't get the right solution, okay? So sorry if I took a little bit more time. I'll give it back to you Monday. I promise. I will have a great weekend, guys, okay? Did I forget the attendance sheet? No, right?